there's quite a interesting future ahead of us. And that is really bringing the two fields of machine learning and simulation closer together.
Welcome to a brand new episode of our podcast, Human and AI, Mind, Machines, and the Gradient Descent.
Thanks for tuning in again. It really means so much to us. We are Uli and Avery, and our today's genius mind is Dirk Hartmann. Welcome, Dirk. Can you maybe describe yourself in 1 minute? So who are you and what are you currently up to?
So my name is Dirk Hartmann. I'm a senior principal in corporate technology. So actually, genius mind, I like it very much because that's in the end what it's about. Yes, it's about to bring new impact into the technologies Siemens is selling to their customer, to the technologies we're using. And the core technology I'm responsible for is simulation and digital twin. So what is that? So actually simulation is more or less the same as machine learning. So we try to predict things, but instead of using data, we base that on physical models and leverage, so to say, the engineering know-how we have and to validate the performance of the assets Siemens is selling.
Then we have an expert, right? I had heard rumors that we are living in a simulation. What's your thought? Are we actually part of a simulation? Can we prove that we are not?
Well, that's a good question. So I think if you look at it, in the end, we are part of a simulation, yes? Because we look at physics, we look at the nature, we extract the physics laws out of it, and then trying to predict the future as good as we can and map that to what we observe, and very often it fits. So you can also say that that is a kind of simulation, but the rules behind we are not really discovering. Yeah?
Is that doable? Would that be imaginable that this entire world we live in would be a simulation? Can we prove that this is not doable in terms of computation, in terms of complexity, or is there just nonsense of the Elon Musk realm?
No, honestly, I think it's of course, I mean, the sheer computational power you would need is at least not available today. But it's a very philosophical question, and I think everybody can interpret it as he likes to. Some of the movie makers are suggesting it, yes.
You just said that you're a principal at corporate research. What is a senior principal actually doing?
So the key aspect is really pushing the next generation of technology. And well, that's easy to say, obviously. But if you look at technology, what's happening right now, so far in simulation, but also in artificial intelligence, we've lived very much on leveraging Moore's law, getting an exponential increase in terms of just the computational power. But what only a very, very few people know is that there's also an exponential law on the algorithm side. So also the capability of algorithms grown exponentially in the last decade. And so the key focus is what we're trying to do is to leverage that exponential increase and just enable new applications. So today we're really at a very, very interesting time because we can really go beyond classical applications, which for simulation was mostly in design and engineering, and open up new paradigms for how we operate, for example, our equipment.
What brought you actually in the field? So before we dive into a bit of the interesting cases you're currently maybe researching or driving or you have already enabled, what brought Dirk in the morning up and into the field?
Well, it's a very long story. So actually what brought me in the field was the book of Stephen Hawking, A Short History of Time. So my ambition was always to study with Stephen Hawking. And then I went actually to Cambridge to study with him. But all of a sudden, going to Cambridge, recognized the field of applied mathematics and found out that, with bringing together these physical models with computations, you have a very, very efficient tool at hand to predict experiments, to predict how engineering system works. And that is what drives me. How good can we predict the behavior of or the outcome of physical systems and use this to optimize products as well as operations?
Do you see a potential for the current situation of corona, of the virus, that we could use those simulations to maybe test the treatment or maybe better understand the virus or other diseases?
So actually, if you look at it, I think there's quite a number of simulation fields currently used and trying to look into it, how it can help to influence on the one hand side or to reduce the spread of the virus, as well as finding cures. And that is really a very, very broad aspects. On the one hand side, you can do computational fluid dynamics simulation. You see people simulating how people cough, how that leads to a spread of the virus, whether it's efficient to have a face mask, whether it's more efficient to have a larger distance, a smaller distance, so you can optimize that. Can use simulations to predict how people move in the shop floor. Can you optimize paths of people in the shop floor so that they automatically increase their social distance? Then it goes all the way down. How is really the virus affecting the lungs and their ability to take up oxygen? Can we simulate the airflows within lungs and consider out of this treatment? So how could you better provide air to people having COVID? And of course, all the way down to finding a cure. So can we simulate in the virtual world, or actually we do it, not Siemens, but researchers outside, how does the virus dock to the cells? How can we inhibit these actions? What would be potential drugs to be used? And can we do that in a large-scale screening using simulations rather than doing experiments? And obviously, the idea is if you do it in virtual experiments by means of simulation, then you're much faster than doing real experiments.
Yeah, that's true. I have the feeling when you look at the data available around those pandemics, it seems to be not that many stable modules and not that many evidences on data that you can use for building a stable models are out there. I was quite surprised, actually, isn't it? On reference on activities you do, because obviously exit log has an impact, right, on your simulation, I guess, on the spread, right? And as comes again with the mask or not mask and whether which districts. And I thought it's not a lot of data that can be actually being used for such models. Is that a typical thing in the simulation domain, that you have a lot of preconditions you have to come up with in order to get going?
I guess it is the same as if you're in the data field, yes? All depends how good is the data you have. But then I think a key point is to distinguish, is it really about validating and proving that a design holds, that a strategy is so and so efficient, or whether it's about finding an optimal strategy. And while obviously many models are, we don't have the data to do quantitative predictions, I think we do have the models to test the various hypotheses. So what would happen if I would increase social distancing? What would happen if I reduce likelihood of getting affected by wearing masks? And then you can compare, of course, always in the context of a model, and then there's uncertainties with the model, but it gives you a good fact-based ground to do decisions just by comparing the different scenarios. And you might not be able to get a quantitative prediction, but a good qualitative assessment of what is the more efficient strategy.
And you're currently in Princeton in the US. So how are you perceiving the coronavirus there? And what are you doing to stay healthy and productive?
Well, I guess that's actually the same as everybody is doing in Munich, yes. So it's all about digital collaboration. So I wouldn't say that's probably not a big difference around the world, how we're working and how that's affecting our life.
So let's move from the theoretical world maybe to the real world. So can you maybe share some use cases of projects that you're most excited about and a couple of ones that you maybe are working on right now?
So there's actually the project I'm most proud of is going back a little bit to my statement at the beginning, trying to use mathematics and new algorithms to take the use of simulation out of the place where it's today and enable things you would not think about before. And that's two fields. The one field is to bring it to the very, very early design stage. So where you can use simulation, give it to a CAD designer together with an optimization algorithm, and it comes up with optimal shapes for certain tasks. And so you don't need any more a simulation expert, but rather the designer can use simulation combined with optimization to come up with optimal designs. And optimal designs in that sense, because the simulation are not that accurate, you have not yet gathered the data through the validation. So it's really more a qualitative comparison between different designs, and thanks to this he's able to choose the optimal design. That's something we are still currently working on, but which is making its way into the products, and we'll see first product releases end of this year, starting next year. And the second big field is trying to use simulation during the operation. So using simulation and run the simulation in parallel while let's say an electric motor while it's operating, and can use the simulation to infer values, thermal values in that case, inside the motor, which you could not access using sensors. And that way, it's an ideal combination to classical or to machine learning approaches, and just giving new sensor values, more accurate sensor values, which you not have access before. And then you can think about completely new operation strategies. That was an example of the motor. You can use the same approach in the context of robots, and using it, we could, for example, teach a robot how to do milling tasks, which everybody thought before, that's not going to work. But really having this simulation parallel to the operation combined with optimization, we could bring down accuracies to 0.1 millimeter, and that's in an industrial scale. And before it was a millimeter, and it was not possible to use it for industrial milling tasks.
That's amazing, right?
Yes, but still, the question was also, what is the future bringing? And I think there's quite a interesting future ahead of us, and that is really bringing the two fields of machine learning and simulation closer together. And people were doing a lot in the past years trying to combine it, but with either, let's say, you use machine learning to train some new parameters for your simulation model, or vice versa, you use a simulation model just to have additional data for your machine learning model. But in the last 1 to 2 years, there's a completely new field emerging, and that's called physics-informed neural networks, where really people trying to bring together those two fields, and you bring the physics information into the architectures, into your functions you're learning. You try to extract latent spaces out of neural networks to learn physics models. It's a vast new field with lots of things happening, and I think that's a very, very bright future we'll have, and that's a core topic I'm right now working on.
Yeah, that's amazing. So if you give a suggestion for the audience out there, right, where should they get a hands on and more information about this field of physics? Simulation meets AI, physics-informed neural networks. Are there some conferences journals or people you knowledge, or is it like, hey, this is a great start for people who want to get in the field of in the section of simulation and AI?
Well, I would say one of the visionary guys behind it is George Kaniadakis, who is at Brown University. And so obviously also coming here, I'm trying to start up some collaborations with him. It was really him who coined this term physics-informed neural networks 2 or 3 years ago. And that's probably a very, very good starting point if you look for one of the researchers driving that field. In terms of conferences, if you look out there, there's not much yet happening. I think it's still very much the mathematics community trying to push to integrate more neural networks in their conferences, and probably vice versa. So at the last International Congress of Applied and Industrial Mathematics last year in Barcelona, there were quite a lot of people, looking at these things. The number of lectures was exploding. Pure conferences in that field, I think we'll only see next year. And then one of them I'm trying also to support from the advisory board and scientific committee to get something going in that direction.
If you look in the field of pure AI, let's say machine learning AI, right? And are there any breakthroughs the last year where even an inglorious mind like Dirk, right, would say, wow, pretty awesome, even though you're coming from a simulation, from physics-informed aspect, where it's like, oh man, this one-trick pony machine learning thing, deep learning aspects, right, really a magnificent success story. Is there something where you say like, oh, that was really, considered as for yourself, right, somehow a breakthrough or a crazy innovation?
What I find most impressive is autoencoders and what's happening on the autoencoder side, because this is really what the physics is about. Yes, you have so many observations around you, but the quintessence is really the low-dimensional latent manifolds you would like to get, because that's what physics is about. Yes, Newton was lying under the tree looking the apple falling, so he sees this video or how that thing is falling down, and to extract out of this Newton's law. So force equals mass times acceleration. That is a low-dimensional manifold. And how can you automate that? And I think that is where autoencoders will play a crucial role, and are a very, very important ingredient.
I think it was even in home office, Newton, wasn't it? Perhaps Latin said it, right? I think it was, passed, right?
I'm not sure whether it was that specific law he invented there, but I think some of his great things he developed while being in home office, yes.
Do you think that simulations have the potential to make our lives easier in the future? For example, Google currently working on an AI model that allows to nearly instantaneous, how they say, to predict weather forecasts. And maybe that can help us to tackle climate change.
Well, the question is whether it makes our life easier or more complex. So if you speak about climate change, yes, then the models can be only as good as the data is. And looking at the current situation, you see there's a lot less planes around. So our data is going down because planes used to be a very important source for getting weather data. So now we need all this data because, that is what we've built on top of. And so I think the more models we get, the more data we need to get those models reliable. And so that's why I think really an art is trying to identify simpler models to predict things, and not just like having more and bigger models is the key. And again, that would be a role where autoencoders play a role to really get the quintessence out of these big models to do predictions more reliable.
Yeah, one aspect is also a pretty hippish are currently generative models, right? Generative adversarial nets and generative modelings itself, right? What's your stake on that?
My stake is simple. I'm not an expert in this field. I have a couple of colleagues who look into this and use this to actually generate structures. So you teach networks in a way to come up with novel designs just by learning from designers or learning how they perform combined with the simulation. So I think it has a bright future, but I'm not really the deep expert to feel sufficient enough educated to comment on that.
And if you want to give the young folks, the very young folks, right, a start. At the moment, a lot of aspects is driven by upskilling, reskilling, right? Everybody, maybe had some few on machine learning, played around with online nets and GitHub. Is there at the same time as, there's an open source movement on TensorFlow, PyTorch, these software development kits, actually quite a community around there, and young guns from college, high school, but also early, university students get their hands already, getting dirty to machine learning. Do you see similar kinds of enablement open source movement in the simulation space? Is that a similar, movement or mindset?
So I think a key difference to the simulation space is that the simulation was originally and still is to a large extent used for validation. And of course, if you do a validation, and my favorite example is always airplanes. So parts of the validation process in airplanes, when you look at the mechanical stability, people use code which is the 50 years old. And just for the sake, because the code is trusted. And so trust is an important asset here. So that's why open source has a hard time to get into industrial applications. Obviously, it's widely used in the academic community, but to get into industry, I think there's a big barrier in terms of this trust validation. That's probably the big difference to the machine learning codes.
That's very interesting.
And obviously, also the level of degree you need to understand from physics and mathematics to use simulation is quite hard. So if you think about you would like to predict an airflow, then you roughly need an understanding what is a Navier-Stokes equation, which is typically nothing being taught in high school. Whereas I think if you play around or use neural networks, it's much easier to get a solid understanding how these things are working to play around with them.
Mm-hmm. So what kind of recommendation would you set for, how do we keep update with the community? How do you keep update? How do you learn? Is it the online courses you can motivate? We've seen a lot of in machine learning is like ArchiveX, right? Like an online, repository we can upload. We've seen, I think the rough number is 200 machine learning centered paper a day, right? Something around there. It's just uploaded, maybe even more, right? So it's really, we have hard times catching up with the latest advances in there. What is that to do your field? How do you keep update? Are there certain Coursera, Udacity courses you say like, hey, this is marvelous, you can recommend for the community out there?
Actually, my favorite source is conference presentations being recorded. Obviously, if you'd like to get into the field, then it would be a Coursera course or any lecture recorded on YouTube. Actually, my favorite one is Learning from Data, which is a Caltech online course. And I think it's a quite good combination between what is the mathematics behind and what are actually, the various machine learning techniques built on top. But all the rest is really, there's lots of great conference and workshop contributions outside being recorded. And now with all the conferences being held in virtual, that is growing exponentially. Yes, so it's actually a great time to get great recorded talks.
Thanks for that recommendation. But a look at the time tells me that we may need to come to an end very soon. And we have prepared a little game for you. So I will start with a sentence, and then I would ask you to just complete it. So Siemens is
a very visionary company which is really trying to reinvent the way how we digitalize industry. And actually, if you look to the outside, many companies are trying to copy our strategy. And so that makes me really, really proud to work for Siemens.
I like that. My optimism comes from?
Well, enjoying life. And I think if you're a pessimist, it's a hard time enjoying the life. So better be optimistic.
Very true. My personal mood shot is?
Combining physics and machine learning in a way that it's usable in industry.
Wow. Thank you very much for your time and for your inspiring insights. It was a lot of fun and it was very interesting listening to you.
Yeah, thanks, Dirk, for much of, giving your view, bridging the world of simulation and digital twin. And folks out there, stay tuned. There's so much to come. Stay bold, committed, and open-minded. And we hear us at the next Siemens AI Lab podcast.
Thank you.
Thanks for having me.